Once again, we'll be working with distance, rate, and time. So here we're looking at the movement of an avalanche. And so what we have here is we have a source area, and so things discussed in G107 are we have erosion or weathering, which breaks up sediment, breaks up stuff, and then we have transportation and eventually deposition. So just like anything, like moving rivers, like moving air, i.e. wind, we can see moving earth via a landslide also has those same characteristics as far as the source area, transportation, deposition. So let's look at a particular landslide and try to understand, well, how fast do these suckers move? And to do this, we have Yungay, which is a town, a city here on the left-hand side of this particular image. And on the right-hand side, we've got the high point, the upper levels of a particular mountain. And essentially, the arrows are showcasing the path that an avalanche and a landslide that was essentially triggered by an earthquake that happened off the Pacific coast here, off of the country of Peru. What we have here is we have a massive landslide. So it went through this particular path that we can see here. So the shortest path, let's just measure it using the scale and find out how far it went from the H, the actual origins, to its destination in Yungay, and essentially buried a town of entire 20,000 people alive. Imagine that, a landslide moving so fast that it buried 20,000 people all alive at one time. Here's a topographical profile, and so this is something you'll be seeing similar later on in this lab that shows the path of this particular landslide from its source area down through to the city of Yungay. And so essentially this is a topographic profile where we're now looking at the side view of this particular mountain slope. So that's once again something you're going to see a little bit later on in this lab. What do you do when you have a landslide that buries 20,000 people alive and just a few people have the opportunity to run up to the sides of the valley and essentially watch the landslide bury their entire valley and their city all in this one big swoop? You just put a monument on top because you just essentially leave those people there. So essentially this monument here is a very sacred site. It's like their 9/11 for this particular area of the world. And so for them, this is just they put a statue on top of the landslide and all of the people here that were buried alive, which we can see here. And so this is a very school liberal artsy thing to do. So we look at the physical geography components to it, landslide, the movement, the rate, and all of that. But also there's some social stuff going on. There's some cultural stuff going on here, and trying to understand how we memorialize place, especially from a natural disaster of a huge magnitude. In the previous lab, I've already mentioned distance, rate, and time, so if you're just slow or not following along, here's another chance to identify how to find the rate or pace of something. Here we have image 1, so you're going to have to do deductive reasoning, you're going to have to do other research, you're going to have to think about things. And so, unfortunately, not every time will your lovely professor give you all the answers. You're going to have to work for him and actually find the answers. And so here we have particular patterns. So then look it up, look at an atlas, look around, do some Googling and find out, well, what might be some key reasons that underlie or explain why certain areas have higher landslide risks compared to others. Next up, we'll be working with topographic maps, which we can see here. We've already worked with those in the previous lab. And so once again, what they are is all points along the same line, just like our isotherm lines. Now, all points along the same line are the same elevation. So with contour lines, we measure elevation instead of temperature, like we did in a previous lab. So for example, here, over here on the right-hand side, you see New York Street. So you see the words New York, and you see that 700. So that 700 means all points along that line, if you follow that long line around all the way till it goes through the med-center, goes all the way up to the VA hospital, you'll see all points along that line are 700 feet above sea level. Further, we got lines that are either to the left of it or the right of it, or either higher or lower. For example, we see 690 shown there. So this is a map that showcases elevation, which we can really see clearly here. Notice on the map here, on the top and the bottom, the numbers get higher as you go closer to the top and closer to the bottom. In other words, the numbers get lower the closer you get to the middle of the map. And so essentially what this is showing is a valley. And so you can see the lines when they're very close to each other. What that means is a very steep slope. As the line gets farther from each other, that indicates more of a flat surface. So essentially we have this aerial photo, this aerial map in which we're looking at the contour lines of a particular valley, which you can see there clearly, in which at the bottom of this valley, or in the middle, is that island lake. So if we look at it from the side view, we would then begin able to see that steep slopes on both of those sides. And so now we're looking at the side view. Now we're looking kind of at the cross-section view. And now we can see this valley much more clearly. And so previously, in the previous image, what is up to the right was in the bottom of the map. And what's up on the left-hand side was actually on the top in the previous image. And so now we can clearly see that those lines, when they're closer together, steeper slopes, as they get farther apart, they start to lessen the slope, starts to get flatter. So we have 9 rules of contour lines. Here are the rules. Now we have our different rules, and so just follow these rules. I'm not going to go read them off to you. I'm pretty sure you guys can read, but for our purposes, some of the things to really focus in on, once again, closer to the line, steeper the slope. Further, whenever you see the concentric series, let's go to number 7, concentric series of closed contours. That's going to, kind of be rings. That's going to be representative of a hill or a volcanic island. And guess what we have for this exercise? An example of a volcanic island. Further, contour lines with tick marks on the inside of an enclosed circle indicate a depression. So that's one of the challenges is if you have all these circles, it's very easy to see slopes and easy to see places that go up in elevation. But what about depressions? And so depressions, get some Prozac, that might help. But first off, depressions, what you'll notice is you'll have these little tick marks that come in from that particular enclosed circle. And you'll see what I mean at the end of the lab when you look at these different illustrations of contour lines and physical features. Finally, whenever you come across a river, and that's something that's going to be pertinent to a future question here, whenever you come across a river, what you're going to do is you're going to have these V's, or the point of the V facing or pointing upstream. So as a contour line comes in contact with a river, essentially it then has a V shape, and you'll see this on the future example, that points upstream. So here we have our image 2. And so what we have is we have our stream, showcases that black line from the middle of the island and goes all the way up to the northwest to the mouth of the river, essentially where the river meets the ocean. So our island, we have all of these individual locations as far as their elevations shown. And so we're going to have to now draw an isoline map. Further, we have the line that's 0 shown as the outside line because, of course, this island is at sea level. So that outside line would be representing 0. So we already have one contour line drawn, and that's the outside line, or essentially the border of the island. So what we're going to do is, because we have a contour interval of 50, we're going to be drawing the lines for 50, 100, 150, 200, 250, 300, 350, 400, 450, and that's it. Why we stop at 450 is because we can see the highest elevation found on the map is 480. We can't go higher than that, so we can't draw the 500 line. So the highest line we're going to be drawing is the 450 line. So that's what you have to consider when you draw these lines, and make sure to use pencils. You will make mistakes, and even further, make sure to use a sharp pencil because you will have to make very precise and specific lines, especially as you get closer to the top of the mountain. So we're going to make lots of mistakes. That's okay. It's, we're millennials. We're okay to, we're used to making mistakes and still getting trophies. But what you're going to do is you're going to draw concentric rings, and it's going to be very, very challenging. And so this is one of those things where this is a particular part of a lab that's been around these labs in G108 at IUPUI for years. So you can sit in the corner, you can mutter things under your breath. It's just loud enough so I can hear you on the other side of the room, but I don't care. This has been in the lab for a long, long time. It's extremely effective for teaching the ideas of contour intervals, which you'll definitely do for a future exam. So we'll go ahead and we'll put in our first contour line. So I went ahead and I'm drawing the 50 line for you. Notice how when I drew this line, I had to consider different locations. And so, for example, making sure that on one side of the line, all the numbers are less than 50, and then on the inside of the line, all the numbers are greater than 50. And you can already see on the left-hand side of this island, you see the 120 benchmark, the 120 elevation X there. So that means I'm going to have to also squeeze in the 100 in between the 50 line and the 100 line. So as you draw these, you have to start planning out ahead. Further, if you go ahead and look at the contour line as it comes up to the stream, comes up to the river, what do you note? You'll see that it has a V shape in which it's pointing upstream. So it's pointing upstream, and so that's something you'll have to do. And so it's similar to what I did there for all the various contour lines that you draw. Here we have the view from the top view, though. So what we're going to do next is we're going to now look at the side view. So essentially we're looking at the aerial view. Now we're going to look at the topographic profile, which, if you can recall, in the earlier illustration of the landslide, I showed beforehand as far as the mountain, its slope going from the top right-hand side down in a previous image. All right, so let's do it. Let's use the contour map, create a topographical profile. All right, so let's get to work here. So we have our image here. So yours will be completely filled out. So your map of your image 2, and we're going to be using that in our topographical profile. And so we've got our elevations over here on the left-hand side. So let's start putting in the information. So what I did was I kind of traced the general outline of this island. So I went ahead, and what I did was I went down to the scale. We see the scale at the bottom of the image 2, the 0, 500, 1,000 feet. So I just essentially used that mark for 1,000 feet. Let's see how far this river goes. And so I got 1,000 feet, 2,000 feet, 3,000 feet, 4,000 feet. Looks like a little bit more. So we're going to go ahead and say we got 4,200 feet from the origin of the river to the mouth of the river. So that's shown at the bottom of this particular topographical profile. And so the on the left-hand side of the axis, or the axis that goes up and down, that's showcasing elevation. Whereas at the bottom we have the horizontal distance the river travels from its origin, i.e. 0, to its mouth, to the destination, to the ocean, which, as we said, is about 4,200 feet away. And so we can go ahead and we can start putting in different places, different dots on our topographical profile. 3 of them are already identified. First off, we got the first one, which is at the top, and it looks like it's somewhere right around 450. So the origins of the river is somewhere right around 450, and so we have a dot. Let's go ahead and put it on the topographical profile as I did there, as it's shown in light blue. Second, we have the orange dot. That's the mouth of the river, which is at 0 elevation, but it's 4,200 feet away from the particular mouth of the river. So it's actually, we can go ahead and put that orange dot there. And so we have our first 2 dots. The first one and the last one already put down. Now we have to apply and see and figure out all the in-between parts. And it's very simple to do that. What you're going to be doing is you're going to be using your contour line. So use your contour line. So the contour line that we've already drawn here, the red line, is the 50 line. So there's the 50 line. So we're going to be drawing something there along the 50, on the left-hand side, the 50 elevation, something across that line. We're going to put a dot somewhere along there. And so if we look at our river, if we go up and look at how far away it is, it looks like it's just before 3,000 feet from the origin of the river. And so we can see that there, somewhere there's the blue area. And so let's go ahead and put the blue dot, like I said, somewhere on the 50 line, but just before 3,000. As we can see, that red line there, the contour interval line that showcases 50 feet in elevation, is just before the end of that black line, which showcases 3,000 feet. And so essentially we now have built up the topographical profile. So what you're going to do is you're going to then, for the 100 line, the 150, the 200, the 250, the 300, the 350, the 400 line, you're going to then be putting a dot, as that once again is your contour line that you drew on the island. Is this going to be then superimposed or transferred over to the topographical profile map? Then you connect the dots. So here, once you put in all those different elevation, those dots for each of those contour lines, you're then going to connect the dots together to form the topographical profile. So you have a perspective as far as where we see flatter slopes or smoother slopes, where the slopes are steeper. Next up, the question will ask, what is the relief of the map? This is, once again, a very simple question. It's just the highest elevation minus the lowest elevation. So the highest elevation, 480 feet. We can see that's the highest number anywhere on the map. The lowest, 0, the shoreline, and that's going to be then 480 feet as far as our relief of the map. In terms of calculating the gradient, we did this in the previous lab, so we'll just continue on. So once again, elevation difference over horizontal distance. And so here's the formula here, the end height minus the beginning height divided by the end distance minus the beginning distance. And so as we mentioned beforehand, we started at an elevation of 450 feet. So that's our beginning height. Our end height, where the stream ends, the river ends, is at 0. It's at the shoreline. And so we then fill those numbers into our formula. Further, we have their end distance, as far as the distance that the actual river ends, is 4,200 feet away from its source, which of course is 0, the beginning of the distance. The beginning of the river. So it's its distance, its origin. So we just essentially do simple algebra, simple math, yada, yada, yada. And so essentially what this says is that means every 1 foot of distance traveled from the source, the river is going to descend 0.1071 feet. We know it's descending because that negative number equals negative 0.1071 feet per feet. And so if it was a positive number, it would be going upslope. Now in terms of the azimuth direction, so we just get out our azimuth, and I just went ahead and I did that for you. And so the azimuth is we'll get that circular device, that compass device, and essentially we put it so at 0 and 360 here at the top, 180 at the bottom, all of that. And so now we place the azimuth or the compass on top of the origins of this particular river. So the origin is the particular river, and so from there, just draw a straight line from the origin to the destination, and we can get the general direction that this stream went. The stream goes. It's not dead, it's still around. And so what we're going to do is come up with a number somewhere between, obviously, 315 and 330-ish. Finally, here are different landforms, and once again, if you look at E, I'm going to go ahead and give you an answer. Those are those tick marks I explained beforehand. So those are little depressions. So what makes those not hills, little bumps up, is the fact that there's those tick marks, which showcases depression. So there in letter E is depression, i.e. sinkholes.